American Axle and Manufacturing, located in Detroit, in Michigan. He received his PhD from Department of Mechanical Engineering at Wright State University in Dayton, Ohio, and his current focus areas include welding fatigue, distortion, and structural optimization. And today he will present weld life prediction using Verity for automotive axle components. Please join me in welcoming Anup on the stage.
Thank you, Pavel, for the introduction. Thank you, everyone, for attending this presentation. I'm Anup Vasu. I'm a senior analytical engineer at the Product Development Department of American Axle. Today, in my presentation, I will discuss the capability of the Verity software in FESafe to effectively predict the life of welding components. Welding joining process is one of the most commonly used in automotive industry, because of it's easy to use, and also because of lightweighting, it can be very cost effective. But at the same time, the weld prediction is a very complicated process because of the presence of residual stresses, there is distortion effects, and so much uncertainty in the geometry. In today's agenda, I will start with the overview of American Axle, followed by a background of Verity structural stress method. This will be followed by the correlation which we observe with multiple automotive axle components. And I have two cases which I feel interesting for all the CA users here, where I call it best practices in related to the weld sizing and also the load if it is compressive nature. And finally, this will lead to the crux of my presentation, which is to detail the significance of shear components on the axle. And I will wrap up the presentation with the summary. So American Axle is a Tier 1 supplier of driveline and drivetrain components. It's established in 1994, and it's headquartered at Detroit. We have more than 100 customers serving the world's leading brands. There are more than 35 facilities, and which is located in 13 countries, and we have more than 10,000 people working for us around the globe. So the Verity module in FESafe is able to calculate the structural stress which was developed by Vettel. Compared to the extrapolated stress-related approaches, it uses nodal force and moments to calculate a traction stress component. Because of this, it's generally mesh insensitive as long as we are able to represent the geometry well. And it had been validated for different geometries, different programs, and different sizes. So this mesh insensitivity is especially useful for us because we have the axle components, full axle components, which can have millions of elements and 50 to 100 welds. And the usual process can be really time consuming. By using this process, not only we are able to run such a complicated process, we'll be able to use one model not only to run a welding analysis, but we can use the same analysis to do structural analysis as well of the components. So the Verity had been applied to multi-axial fatigue and had been adopted by ASME and other standard organizations. So here I have an example of a butt welded arrangement. So we have a hypothetical crack plane which is represented by the XY plane, and the very complex stress distribution because of the notch effects can be simplified to a very simple stress state, which can be represented by a membrane and bending component. So there are three kind of traction stress components. There is a normal structural stress component, there is in-plane and transverse shear. The normal component represents the mode 1 failure, the in-plane shear represents the mode 3 failure, and the transverse represents the mode 2 failure. So Bethel did thousands of test data, and most of the cases were related to mode 1 failure, which only one component was required. That was the normal structural stress component. And when they used the thickness and loading effects, they were able to reduce the scatter in the data significantly. This IR function, or the load mode function, has fracture mechanics background, which is generating a bending metric, which is calculated from a 2-stage crack model. So, but that does not mean that it can be applied to all the cases. Let's say if there is a case of torsionally dominated loading, or maybe even a pure torsion. So in those cases, we might need to include the shear components. So from the distortion theory hypothesis, we have the von Mises form of the structural stress, which is shown as the effective structural stress range equation, which we include the in-plane and the transverse shear component. And by including the thickness and the loading effects, we'll be able to calculate the effective equivalent structural stress range equation. So on the left chart below, most of the cases are pure torsion and torsionally dominated cases, where we were able to obtain a very thin band of data. So once we have this data, we, compared to our nominal stress methods, where we have for each and every load cases and the joints, we have a separate SN curve. The beauty of this method is that we only have one SN curve. And the blue line indicates the mean, and the pale line indicates the variation band of the data. Some other unique advantages of this process is we don't have to worry about the separate representation of the base material or heat affected zone and the weld material. Also, the yield strength is not a factor. There is a multiple tests done on different grades of steel up to even 1000 megapascal, and it found that one curve will be able to represent the entire case. And also, the tensile strength has very minimal effect. So for all those cases, we will be able to use one curve, and this curve is this master SN curve. So now let's look into the test cases we ran and how we did the correlation. So our first case is for a constant amplitude loading scenario. So in the x-axis, we have the measured weld life, and y-axis we have the predicted weld life. And we have more than 10 cases here. The blue line represents the mean, and the dotted red line denotes the variation band. So for these cases, which are very different in nature, we are able to observe very good correlation with the test within the variation band. So let's look into the detail of these cases. The PTU means a power transfer unit, which we'll discuss in the next slide, and there are bracket welds also, which we'll discuss in the next slide. So some of the loading cases are vertical load. Vertical beaming load is a load which your vehicle, when it encounters a pothole, experience. There is the fore-aft load. When you are braking, what is the load experienced by the axle? Then there is the shock bracket load, which is the load through the shock bracket, which comes through the shock absorber. Then there are so many different loads. Even there is the torsion load for which a brake flange which is applied on a brake flange. So multiple cases, multiple programs, all being able to correlate within a simple variation band. So we see good correlation with the constant amplitude loading scenario. Now we look into a variable amplitude loading scenario. So earlier we were talking about this bracket well. So here on the top picture right, we have a rear axle, And the bracket valve we are talking about is on this is a shock bracket valve, which is the failure mode which we are able to predict using this verity technique. And this green component is this carrier which holds the differential, which allows to rotate the wheels at different speeds. So for this case, by variable amplitude loading, we have something called time history. So during the entire vehicle's life history, there is multiple load paths through, let's say the weight of the vehicle is on this particular bracket. There is the weight coming from, load coming from shock absorber. All these load paths are acting at the same time, and we are able to match, as you can see this rose dot, we are able to predict within the variation band. And the second case study is a PTO power transfer unit. So it's a power transfer unit component. So the power transfer unit takes the power from the transmission and transfers it to the rear drive. So this is one of the system inside the power transfer unit where the load is coming through the helical shaft, and it's welded through a hypoid gear shaft. So we are talking about the life of this valve, which is circumferential in nature, and in the case of the rear axle weld, it is a fillet weld. So in both these cases, we are able to get good correlation within the band. So one thing to note is that using this verity technique, there is different kinds of weld. Let's say close weld, in this case like a circumferential weld. There is the fillet weld, then all these kinds of weld and the different loading conditions, we are still able to get good correlation. But there is much more in detail to discuss how we are able to correlate for this kind of axle components. So that brings me to some of the best practices which can be very useful for the CA engineers. So we already have certain practices which we might be able to see in the manual, such as wrapping around the weld, which the weld end failure is one of the most common failure mode. So by doing a wraparound, we'll be able to capture that effect. So in this case, I am going to talk about the effect of weld sizing and also how the mean stress might be able to affect. Maybe Dr. Hong will have additional comments and suggestions, so I will leave those additional topics for him. So the first case which we are talking about is the effect of weld sizing. So in this case, we look into the plot on top left-hand side. So it's not very clear. So the x-axis represents x by t ratio, where s stands for the weld leg size of the weld, and t stands for the thickness, the plate thickness. So what we observe is that, and the y-axis is the stress concentration factor. So there are three lines. So if you can see, if the s by t ratio is greater than, in this case, 0.8, we see that it can be toe failure. And if it is less than that, it's highly likely it can be a weld failure. Weld failure can be root or throat fracture. On the right-hand side, we show a case where we'll discuss in the later slide where we had a throat failure. So what this means is that, the size of the weld can be has a critical part to play in first predicting the life, because the weld toe failure is the most common failure mode, most preferred failure mode, I should say, because there is so many inherent defects along the throat, along the root, so which we might not be able to represent very well. So we should try, to model for the weld toe failure. So does that mean that we should have very high weld leg size to prevent the weld root failure? So, but that can create additional problems, such as maybe distortion problems, or maybe even can affect the light weighting. So that is where we have this chart below where we can talk about the critical weld size, how we can define a critical weld size. So x-axis represents the total penetration of the weld through the thickness of the material, and y-axis is the effective S by T ratio, or the weld size ratio. So from this plot, what we can observe is that if we are able to get enough penetration, still we will be able to use a smaller weld leg size. So this is very important because in this particular case we had a very small effective, very small weld leg size. And as you can see, the penetration is not that high, which led to this throat failure. So it should be a function of the weld penetration and also the weld leg size, which should be carefully considered while looking for the design standards. So my second case is an interesting one, which I think our keynote speaker already discussed a little about the effect of compression. So this had been a confusing thing for quite some time. So in this particular case, we have a butt welded scenario where we are applying a compressive load. So this will be able to generate a compressive stress on the weld, or structural stress I should say, which when we look into the post processor will give you a weld life. Let's talk about an alternate scenario where we are applying a tensile load, which is able to generate, let's say, the same magnitude of the structural stress. What we will see is that the same magnitude of the tensile structural stress will be giving the same life as the magnitude of the compressive stress. So some of you might be confused, but some of you know that is because it takes the effect of the range, not whether the process is compressive or tensile in nature. So, and there are multiple tests which had shown that weld can fail under compression, but the question still remains whether the same magnitude of the compression or tension can cause the same life, because very often in our industry what we observe is that's not the case. When we predict it, we are severely under predicting the results. So there is one suggestion or one way which we might be able to look into, that is to consider the effect of mean stress. So mean stress can rise due to let's say preload, or even due to load, or even because of the presence of even the residual stress can be considered as a mean stress effect. So in this particular case, some tests were conducted and was observed that different kinds of So as you can see from the chart below, if you don't consider the effect of mean stress, then there is significant scatter. And if we include the mean stress term, as you can see on the right hand side equation, we'll be able to reduce the scatter significantly. But this does not mean that this can be applied in all cases, but some cases where you see that it's severely under predicting the result, then this might be a case to look into. Let me talk about the effect of shear components. So first, I have a situation where the mode 1 dominant scenario. So in this case, we are able to predict the location of which weld it's going to fail. And what we observe is that in this particular case, where it's a rear axle where the shock bracket weld is failing, we see it's dominated by normal structural stress. The shear effect is minimum. And we are able to predict it pretty well with the test. Now let's look into a second case where it's a brake flange weld, where it is subjected to a torsional loading. So this is the case where we were talking about throat failure. And in this particular case, we observe that there is a very high in-plane shear component. And there is also a normal component because of the gaps present between those two components and also the non-symmetry of the break flange. So when we compare the life prediction, if we don't consider the effect of shear, we are severely over-predicting the life. But in this plot is like this because it's like a 270-degree well. So, but if we consider the effect of shear, then we are able to get it within the variation band. So what it shows is that we need to consider the effect of shear. Also, I forgot to mention this, we need to consider that this is a throat failure, not a usual way of predicting through the thickness. So we need to understand that this was done through the throat of the weld, not through the thickness of the weld. So if we look into the through the thickness, it will not give you very reliable results or close to the test results. So depends on the failure mode, we should be able to model the weld. And our third case is a transverse, mode 2 load dominant scenario where we have a component which is fixed in the bottom and is welded to the gear and it's pulled axially. We observe that there is very high transverse shear effect. And the preliminary results had shown that if you don't consider the effect of transverse shear, then this will be over predicting the life. And my final slide is discussing the combination of all this, which is a very common scenario in our PTU. So as you can see from the slide, in this case, the normal mode is the most most dominant mode, but the shear, the terms are also contributing to the life. If we don't account for the shear components, then our prediction will be away from the variation band. So in the summary, we learned that Verity can be a very good tool in predicting the life. We talked about the effect of weld sizing and the penetration. We also talked about the effect of mean stress and maybe a way we can handle it. And finally, we also talked about the effect of shear components and how it is important to predict the life accurately. That's all from me, and thank you.
Thank you. I have a question, actually. I don't know, I might have misunderstood part of your presentation, but it sounded like you stated that if you have a shear-dominated welds, the expected failure mode will be a throat failure rather than a toe failure. Is that correct?
No, that is not correct.
Right, okay.
So
my misunderstanding then.
So in that particular case, it was a shear-dominant loading, and the throat failure occurred not because of the loading, it is because of the weld sizing.
Oh, I see.
So
okay.
the weld size was very small, and the penetration was also very small, which led, and because of the loading, if you don't look along the throat, we will not be able to capture the mode.
So you think that the initial statements comparison of the weld size and the penetration would also hold for shear-dominated welds?
All these factors are critical, but this, because at the end, you apply the load. Instead of defining the weld lines across the thickness, we need to know that we are looking only through the weld, not through the thickness. So if we are able to look through the thickness, then we will be able to capture the effect. But if we look through the toe or through the thickness, then we will not be able to capture this mode. So okay. It should be more of a understanding the failure mode, and then we'll be able to capture this effect.
Okay, thank you. Yes. We have a question there.
Yes.
For the variation band, how do you define the band?
So in this case, it was very similar to the master ascent curve, which was 2 sigma. So yeah.
Okay.
Yeah. So it is like 3 times, around 3 times different.
You just define the average line.
Yeah. Yes, that's right.
And that will be from the particular
Yeah, it's from the original, yes, master SN curve, that's right.
Okay, thank you very much.
Thank you.